So far we have been discussing the effect of excitation either in the form of a dynamic force or dynamic moment or some periodic motion to the support of the system of a system, and primary objectives were during these studies that what is the response of the system, which we measured or which we defined through the displacement of the main body which represents the system's inertia. We will extend our studies little bit in the direction which will be extremely useful while designing a system. What we will do now is that try to analyze that if we keep a system which is supported by kind of or maybe a combination of springs and dashpots, and if the ground has some motion, what will be the motion transmitted to the main body? It is something similar what we have been doing in our vehicle example, where the road was wavy and the wheel was moving up and down and the driver along with the car was also moving up and down. So that is one thing. That means the motion of the support or the ground gets transmitted to the main body of the system. Similarly, we should also investigate the situation where a system, mechanical system, is generating some dynamic force, maybe due to some unbalance present. Then how much of that unbalanced force which is produced in the system gets transmitted through the combination of springs and dashpots which we put into the ground. So therefore, what we will try to do, we will try to design our support with the help of a combination of springs and viscous dashpots in such a way that the system is isolated from the environment. That means neither the forces or moments generated in the machine when it runs gets transmitted to the floor, and that way it may affect other precision setups, or if a precision setup is being mounted, it should be done in such a way that all the disturbance which are there in the ground, they do not get transmitted to this. So this topic is generally termed as transmissibility and isolation. The main objective of this study will be how to decide the parameters like stiffness and dashpot, viscous dashpot damping coefficient in a manner so that the system can be isolated from the environment. So we will let us first see the case where so this is the system we have been studying so far, a simple spring mass system, spring mass dashpot system. Now in this case, we have already solved the problem that when the ground has a motion like y cosine omega t, then x is given by so this also oscillates with a magnitude of this. So therefore, we define transmissibility by this quantity. This is the displacement transmissibility, that is x by y, which is nothing but we have already seen this, we have also plotted this. What earlier we were plotting this, the same thing is actually defined as the transmissibility, and it is like this. We have already seen that transmissibility, if we plot against frequency ratio, zeta increasing, and both at r is equal to 0 and r is equal to 0.2, transmissibility is always 1. That means whatever disturbance I am giving, the same amount is being produced here. But if you can design the system in such a way that r is large enough, we are operating somewhere here, then maybe transmissibility will be a small fraction, maybe only 10% of this motion which is being given to the ground is being transmitted. So the other concept of transmissibility is, as I mentioned little while ago, that a system or a machine, when it runs, it generates some unbalanced force. The question is how much force is transmitted. Ground or base, whatever it may be, say it is Ft. Of course, a harmonic function of time, but magnitude is Ft. Then Ft by F0 is called the transmissibility. That is another way of looking at the transmissibility. When a force is generated in a machine, how much of that force goes to the ground through the supports or through whatever arrangement we have made for supporting this system. Now, here let us therefore find out how much force is being transmitted. Now, force is being transmitted only through the elements like spring and dashpot. So, the vector sum of the force at any instant on the dashpot and the spring is the force which is transmitted to the ground. We will again use our convenient rotating approach. So, spring force is represented by this rotating vector. The damper force is represented by this rotating vector leading the spring force by 90 degrees, and of course, inertia force is represented by this rotating vector, and all these three we know that must the whole thing is rotating with fixed RPM omega, and the real values at any instant, as we have been mentioning again and again, are actually the projections on this some reference line. So, if this is omega t, then this will be phi. That means the displacement x lags the exciting force F0 by an angle phi. Now, what is the force which is being transmitted to the ground? Ft. Now, we have seen that Ft is the vector sum of the spring force and the dashpot force. That means it will be represented by this rotating vector, and at any instant this projection will be the instantaneous value. So, therefore, let us now see how much is the transmissibility. Now, Ft is nothing but square root of kx square, this much, plus the dashpot force divided by F0. F0 is again this square plus this square, square root. How much is this? This is kx minus m omega square x, this square, plus this is again so this is the ratio of the magnitude of the transmitted force with magnitude of the generated force, and if we take x common outside, it goes out and it becomes and you definitely have guessed by now that we are going to get the same if we divide by k square or take k square common outside, then it becomes 1 plus c omega by k is 2 zeta r. This is 1 minus m omega square by k is omega square by omega n square, that is r square, and this is again. Thus, the expression for transmissibility, both from the point of view of transmission of motion or vibration or transmission of dynamic force, it gives the same expression we find. So, therefore, it is a very important result of the study of vibration is that we can isolate systems and machines from the environment, so that neither an unwanted disturbance come to our system when we are handling very precision experiments, or the ground does not get too much of disturbance from the machine on which I am working, suppose a very heavy forging machine or machine tool which is generating large force, then a smaller amount is really going to transmit it to the ground. So, that ground will have lesser vibration produced by this transmitted force. So, this technique of isolating a system from the environment is called isolation, and the quantity which dictates to what degree one system has been isolated is called the transmissibility. And for simple systems like this, transmissibility behavior is like this and expression is like that. Best will be perhaps if we solve a problem. So, this is an engine, a vertical engine is supported on a concrete block. This concrete block again in turn is resting on a system of springs with total resultant stiffness of K and system of dashpots total resultant damping coefficient C. The force which is unbalanced force which is developed So, the unbalanced force generated in the engine is given by this expression, where small n is the RPM of the engine. So, this is a simple harmonic force. We are assuming that it is the primary unbalanced force. That is why it is 2 pi n by 60 t. That means it is omega into t. That means it is connected with the rotational speed of the engine, and therefore, it is clear that it is the primary. And the magnitude of the force is also increasing with force, obviously, because the centrifugal force or unbalanced forces will be always increasing in magnitude, not only in frequency, when the RPM increases. So, this tells us the approximate representation of the generated force. Now, we say that at 100 RPM, the magnitude of the transmitted force that is Ft is equal to is 100 Newton. Now, what will be So, if the question is this, that given the information that at 1000 RPM of the engine, the magnitude of the transmitted force is 100 Newton. Then if the engine runs at 1500 RPM, what will be the transmitted force? So, now we have been given that transmission ratio or transmissibility at n is equal to 1000 is equal to 1. Sorry, is equal to 100 is the transmitted, and how much is generated at 1000 RPM. This is 1000. At 1000 RPM, the magnitude of the generated force will be 100. So, also 100 equal to 1. Now, what does it mean from these characteristics? The transmissibility can be 1 only at r is equal to 0. That means the frequency is 0, which is not possible because the engine is running at 1000 RPM. So, the only other possibility is that when r is equal to root 2, transmissibility will be. That means n equal to 1000 RPM corresponds to r is equal to root 2. So, we can find out the or, that means omega n is equal to actual operational frequency omega by root 2 is the natural frequency, and this we know how much is the omega. It is 2 pi into 1000 RPM divided by 60 root 2. This so many radian per second is the natural frequency, or this will be equal to, or even if we do not calculate it unnecessarily. So, therefore, let us find out r prime. R prime will be how much? It will be omega by omega n is equal to, how much is omega at 1500 RPM? This will be 2 pi into 1500 divided by 60 divided by omega n. Omega n is this much. And this will be 2 pi, 60, 100, they all cancelled. So, it will be 15 root 2 by 10, and whole thing is or r prime square equal to 4.5. Now, one point which was missed when we mentioned this, as such, if we just tell r prime, we will not be able to solve the problem because C is not known. So, therefore, the only possibility will be in this case, we can find out the transmitted force as 1500 RPM if the damper is disconnected. In the first experiment, it was not necessary to disconnect the damper because at r is equal to root 2, the effect of damping coefficient or damping factor is not present. It is irrespective of that value of zeta, it is 1. But when you deviate from this, then the transmissibility depends on the damping coefficient, information on which is needed. But in this case, we have not given that information. So, therefore, the problem is actually what we can find out is that when the damper is disconnected. So, in this situation, the transmissibility is given simply by 1 by 1 minus r square. r prime, and this is and transmitted force at 1500 rpm will be now how much will be the force generated F0 at 1500 rpm? It will be simply 1.5 square into 100, that is 225, and transmissibility, sorry, transmissibility will be 1 by 3.5, so much of Newton, approximately equal to . So therefore, you can see only approximately 30% or even less than 30% of the force which is being generated here is being transmitted. By suitable choice of the stiffness, etc., we could make it still less. So therefore, we, for simple situations, a designer should keep in mind not only the design of the machine, but the support system. In the market, actually there are standard isolators available, which are small systems which can be directly placed below a heavy machine which is being placed in a shop, so that the machine is isolated from the ground, not to disturb the ground. Similarly, for mounting very accurate equipment, instrument and such devices, then they are also isolated, so that disturbances present in the ground do not come to the instrument. So I think this brings more or less to the end of our discussion on single degree freedom damped systems. Only thing what we have not done, but as mentioned earlier, that handling problem where a system is subjected to non-harmonic but periodic forces or disturbances, we can split the non-harmonic but periodic disturbance into a series of harmonic disturbances. And as the systems which we are discussing are always linear, we find out the response of the system because of each harmonic, and the result will be the sum total of the everything. So what is really happening is it is a mathematical exercise rather than any physical or mechanical activity. So we will avoid that, because it will be simply a technique which you are familiar with about how to split a periodic non-harmonic function of time into a series of infinite number of harmonics, which are pure harmonic quantities or sines and cosines, and then the magnitude of each harmonic you can easily directly from the characteristics of the system can find out the response, and the total response will be sum total of all the responses. So we will not take up those discussions separately, as except mathematics of or the technique of Fourier series, except that nothing new is there in present. Rather, what we should pick up now is one or two cases or one or two topics which may be very relevant, though always not directly a part of a single degree freedom system like this. One very common problem faced by mechanical engineering is the shafts carrying discs. So, a shaft like this is rotating with a speed omega. Now, whether there is any potential problem, the subject, this dynamics of rotating bodies itself is a subject. We will not be able to discuss it there, but the simplest possible case we would like to take up, because it has a lot of similarities with the things or the kind of analysis we have been doing. So, what are the possibilities is that due to when you mount the disc on the shaft, the center of the disc or the CG may not be exactly at the axis of the shaft. So, if this is the shaft, the CG may be somewhere here. I am exaggerating, but center of the shaft we call it as O prime. Again, because of the centrifugal force which is generated due to this rotating body and which is unbalanced, the shaft will also get bent, and the axis, that means real axis rotation, if you join this, that means shaft will be bent so this is the point about which the whole thing will rotate. So, we will take up the simplest possible case where the deflection of the shaft, then the location of the G and the center of the disc, that the relative position remains same. That means the bent shaft and the disc, they all rotate like a rigid body, and this particular type of situation is called forward synchronous precession, and that occurs very often, and let us see what we can do about it. So, therefore, if this distance is E, eccentricity which is inherently present because of wrong manufacture or fabrication, and this distance is R, or not R, because R may get confused with the frequency ratio, we can use it by rho. Rho represents the deflection of the shaft due to the unbalanced force produced. Now, what are the forces acting? External forces acting on the disc, let us see that. Now, the shaft has been bent. Now, when you bend the shaft, then effectively it is nothing, just like a spring. That means a force will be acting in this direction, and the shaft will act as a spring with an effective stiffness of K. So, this will be K, and the magnitude will be proportional to the deflection of the shaft, which is rho. Then this point is rotating like a circle. So, this point's velocity is in this direction, and the fluid which is there, that is air or whatever medium in which it is immersed, that will produce a drag force whose resultant drag force on the whole disc we can assume logically to be passing through the geometric center of the disc. That is the drag or the friction by the fluid present in this, and this magnitude will be equal to the velocity of this point, which is rho into omega, and the coefficient which we may put C, representing the viscous friction of the surrounding fluid. So, therefore, these are the two external forces acting, and let us look into the dynamics then. So, enlarging this figure, this is O, this is rho, this is E, this is G, and this point is O prime. forces are K rho C omega. This angle is theta, and this also let us consider that this is the rotation from time t is equal to 0. That means when O prime g is parallel to this direction, that is the reference line. So, if t is 0 there, this angle which it makes now with that direction is omega t. Remember, theta and omega t, though they are not same, but the whole thing is moving like a rigid body. So, therefore, we should keep in mind that theta dot is also equal to omega. Now, if we split everything into two components, x and y. So, the coordinate of the center of mass of the disk is xg and yg, and its accelerations will be xg2 dot and yg2 dot, these components of acceleration. So, therefore, equation of motion we can write that mass of the disk into xg2 dot must be equal to the total force in the x direction acting on it. How much is that? One is c omega rho, and what will be the component in this direction? Now, this angle is theta, this is omega t. So, omega t minus theta, omega t minus theta. So, therefore, this is 90 degree minus theta, because this is 90 degree, and since this is theta, so it is 90 degree minus theta. So, therefore, it will be sine theta minus the component k rho cosine theta. Similarly, in the acceleration component in the y direction is equal to minus c omega rho Now, we can also represent xg and yg. Now, this xg is equal to x o prime plus e cosine omega t, and yg yo prime plus e So, this will give me x o x g 2 dot is equal to x o prime 2 dot minus and yg 2 dot equal to substituting these in these two equations, we get Now, C omega rho is nothing but the velocity of this point, and if you multiply by sin theta, what happens? It is the x component of velocity of O prime point. So, it is nothing but C into x O prime dot. I think I hope I am clear. This point is here, its velocity is in this direction, is C, sorry, velocity is simply omega into rho. So, it is two components. This component is nothing but x O prime dot, and C comes there. Similarly, the other one will be y O prime dot in this direction when it is omega rho e C omega rho cosine theta. Anyhow, so this is this, and minus k, and rho cosine theta, since this is rho and this is theta, rho cosine theta is nothing but x component of this point O prime. So, it is simply next, the other equation becomes, I am substituting yg 2 dot by yo prime 2 dot minus omega square e sin omega t, and that is equal to, now rho cosine theta, omega rho cosine theta, here we have found it is omega rho cosine theta is the y component, the positive direction itself. So, minus sign will remain, and rho sin theta is omega rho, rho sin theta, rho is this and rho sin theta is this. So, this is yo prime. So, it is minus a. So, this can be written like this, m x o prime 2 dot plus c x o prime dot plus k x o prime is equal to, I take this to the other side, and this equation becomes and now we remember our solutions to this form of equation. So, we can always write x o prime is equal to, now f0, we have solved this problem, mx2 dot plus cx dot plus kx is equal to f0 cosine omega t. F0 is being replaced by this. So, what we will get here, the final solution, f0 by k, I think that was the numerator, where zeta of course is here is cosine where of course you have to keep in mind r is equal to omega that is the rotational speed, by omega n. Omega n is the circular frequency of natural lateral vibration of this, which you can keep as. And zeta is again, we know zeta is 2 square root of k m c divided. Now, one thing is very clear, that if we want to find out, this is x o prime, this is y o prime. So, rho square is equal to x o prime square plus y o prime square. So, this will give us rho equal to So, we find that the characteristic will be very interesting. Let us see how it is going to be. Now, for omega is equal to 0, this is rho is will be equal to 0, because numerator is 0. As it increases, when omega becomes very large, then r is very large, we can ignore this, and since this is r to the power 4 and this is r to the power 2, we can ignore this. So, after square root it becomes r square, that means omega square by omega n square, that is k by m. So, it will be E. So, if we plot in E rho, then first what will happen when r is equal to 1, suppose zeta is very small, extremely small, so we can ignore this. So, denominator is 1 by r square approximately. So, when r is 0, omega r is equal to omega by omega n. So, omega is 0 means r is 0. So, it starts here because rho is 0 at omega is equal to 0. Then it shoots up when r tends to 1. And then comes down, becomes E. Of course, it is the magnitude I am talking about. If zeta is present, if zeta is increasing, so at very high speed, the deflection will be deflection of the shaft will be equal to the deflection of the, or the error of the center of mass from the center of the actual shaft or axis of the shaft. However, when omega is nearer to omega n, there is a possibility that the vibration, that means the deflection of the shaft will be very large. That means it is something like resonance what we had, and that sometimes be so large that the shaft may be permanently damaged and bent. This particular phenomena, when it happens, that means at omega is equal to omega n, that means if the shaft is like this, then the equivalent stiffness of the shaft here is K and mass of the disc is Km. If this is equal to omega square, or omega is the rotational speed of the shaft, then again something like resonance takes place. This phenomena is called whirling of shaft. This phenomena is called whirling of shaft. It is the simplest possible case of forward synchronous precession, and the speed at which it happens is called critical speed. Therefore, while design, it is essential for the designer to keep in mind, if he is designing a rotating system, that the rotational speed of the system as designed should never go anywhere near the first critical speed or the critical speed of the system. Sometimes when it is found that the critical speed is low and the operational speed is high, for example, like the alternators in thermal power plants, the shaft rotates at a higher speed than the critical speed. In such cases, to avoid whirling and damage, what is done, the shaft is quickly accelerated through the critical speed, so that it does not get enough time to build up large vibration and large deformation of the shaft. So, this is a situation, the simplest situation is very similar to what we get in case of a simple spring mass systems behavior when some damping is there. Now, we have not gone into the details of finding the phase angle and all those things. It can be easily found out without any problem. But the main thing what one has to keep in mind, that a shaft has certain speeds at which the system resonates, causing very large deformation of the shaft from its nominal straight position, and these speeds are called critical speeds, and the design should be such that they should be avoided. At very large RPM, when you operate, the deformation of the shaft will be the amount of error which was there while fabricating the system, that is the key or eccentricity of the center of mass. I think, but this more or less completes most of the things which we are supposed to take care of in a simple system with a spring mass or spring mass and dashpot parameters. It is now important, because a very large number, or rather most of the systems are not, in most of the systems case it is not possible to express or represent the system with the help of a simple mass, and therefore it is absolutely essential for us to now investigate what happens when the number of masses are more, or the degrees of freedom of the systems become more, or the system becomes more complicated. Subsequently, we will devote our attention to systems which higher degree of complexity, in the sense that the number of degrees of freedom will be more.